from this equation, if I move forward, what I will do is, m is anyway a constant, I can take the double derivative outside. So I'll write f over here is d square by dt square. For the complete force which is acting externally, the complete force will be summation of mi into ri vector, right? Where this ith particle is equivalent to the center of mass of the system of particles. Therefore this Ri vector can be written as, in terms of center of mass, it will be the summation of mi Ri over summation mi. This is the formula we use to find the center of mass ka position vector. The summation mi for the complete set of systems will be the constant m, which is the total mass of the system. This will be my capital R vector, which is the radial vector or the radius vector or the position vector of the center of mass. So if I again put this whole thing here, I will get force acting externally will be d square by dt square of m vector, total m, sorry, not vector, m, the total m into r vector of the center of mass. Taking the derivative again inside, I will get f external vector will be m into d square r vector over dt square, where this d square capital R vector dt square represents the acceleration vector. This is acceleration vector of center of mass of the system. So I have got the equation of motion exactly in terms of the center of mass. This is the equation of motion of center of mass. Clear? So now we are done with the equation of motion of the ith particle, which has come similar to the equation of motion for the center of mass. And since we will be applying the conservation theorems over all of these particles, over the center of mass also, over the ith particle also. So for finding the momentum of that ith particle or the center of mass, I can write momentum, which is the p vector will be m into v vector. So here it will be the capital P will be capital M into capital V vector, where this is the total mass of the system. While this V vector, this is the velocity vector, will be the velocity of the center of mass or of the ith particle. So I'll get the similar equations of motions for both of these, but now this is not the velocity of a single particle, but it is the combined velocity of the system of particles which are acting at a certain point or on the center of mass. So for this, if I say what is the conservation theory of linear momentum in case of center of mass, I will say again, if the force acting, the total force acting on the center of mass is 0, I will get dp by dt, which is here the momentum of the center of mass, will be 0, and I will get that even I am studying a system of particles, the momentum of center of mass remains constant. Which is the conservation of linear momentum of center of mass or for the system of particles. I hope it is clear. So, since we are done with the conservation of linear momentum, the next topic is obviously which is the conservation of angular momentum for the center of mass, right? So I will write conservation of angular momentum of center of mass. Right? Now, angular momentum was defined as r cross p vector. Right? P vector ko we can break it in terms of mass into velocity vector. So I'll write Li vector will be Ri vector cross Mi into Vi vector, right? Since it is the conservation of angular momentum of center of mass, that means my torque which is acting on the ith particle, the total component, again just like the linear motion में हमने किया था, if it is 0, which is also equals to dLi by dt, that means dl by dt is equals to 0, right? We are equating this thing. Therefore, I will write dLi by dt will be equals to d by dt of Ri vector cross Mi Vi vector. Taking the derivative inside, since it is a cross product, it will get divided to both of them. I will get dRi vector by dt cross Mi vector Vi vector plus R vector cross Mi dVi vector by dt. dr by dt is nothing but the Vi vector, and Vi cross Vi will always be 0. So I will get dLi by dt is equals to Ri vector cross Mi vector into Ai vector. Since dV by dt is the acceleration vector, what is Mi into Ai? This is the force. So I will get dLi by dt is equals to Ri vector cross Fi vector, which is the normal linear force acting on the ith particle or on the center of mass. And this is what? Tau vector. Now this is the equation of motion of angular momentum of center of mass and its relation with the torque and the linear force acting on it. From here, now I will say that dLi vector by dt is equals to Ri vector cross Fij summation plus Fi external whole vector, just like we did in the previous topic. So we knew that summation of this came out to be 0 according to Newton's third law of motion. So I was only left with Fi. I will get dLi vector over dt is equals to Ri vector cross Fi vector external. During the conservation theorems, we say that the externally applied force is always 0. So this force is 0. So this derivative comes out to be 0. We say Li vector is a constant, which means that this is the conservation of angular momentum of center of mass or the ith particle, where Li denotes the angular momentum of the ith particle or the center of mass. So with this we are done with the conservation laws, the mechanics of a single particle for a center of mass, and we have side by side to a little extent we have generalized it to a system of particles, which in detail we'll be doing in the next lecture. So till here, please go through the previous lectures and these lectures, so that the next lecture, which is a heavy lecture because we'll be dealing a large number of particles and finding their mechanics, you must be familiar with all of these. So with this we are done for today. See you in the next lecture with I hope you are revised with these concepts thoroughly. So thank you. Stay safe, stay happy. Thank you.